So we're picking up with centroids again. I want to go through example D. Sometimes I do this stuff for you guys, although we don't seem to have as much extra time in the classes I would like for you to get up on the board and do things like this. But this is kind of what I expect from you when I give you a problem worked out and I ask you to kind of fill in some of the details. So we're going to try and find the centroid of this region. So we're going to assume that it's a constant density. If it wasn't a constant density, then we'd be finding the center of mass. That's a little bit harder problem. Let's take a little slice through here. Now, one thing that's true about this region that's kind of helpful, maybe you notice it, right here. What's this line trying to highlight? What feature about this is it trying to highlight? It's symmetric. So the x and y coordinate of the centroid are going to be the same. So that kind of cuts down on half of our work here. Now we're going to start out by finding the area between these two curves. That's what we're doing here, trying to find the area. Now it's going to be top minus bottom. You might notice that mine looks a little different than yours. I went through and modified a couple things, added a few more details. For instance, the top curve is the cube root of x. The bottom one is x cubed. And those change places after the point 1, 1. In any case, top minus bottom times the width of this. The width of that is just going to be a dx term. So area is the height times the width. And we'll integrate that from 0 to 1. We end up with a nice even 1/2. But now we want to try and find the moment around the y-axis. So that is m sub y, moment around the y-axis. And then the x-coordinate of our moment is going to be x bar is going to be m sub y over a, where a is the area. So how are we going to find that moment? Well, let's see. Let's give ourselves some coordinates here. This point we can call, say, x and y. And it doesn't matter what you call these points here, but what we're going to need is this distance. How far is it from this point over to this point? Now, it doesn't matter exactly what the y-coordinate is. This distance is going to be your x-coordinate. So it's just going to be, you know, if I was looking up here, this would be the point 0 on y. That distance is going to be x minus 0, or just x. So we're going to multiply that distance times the area of this slice. So basically, the force, which is the area of the slice, times its perpendicular arm here, or the distance to the y-axis. So that gives us x times its area. That area expression is the same what we had up here. So if you put an x in here, we get that expression for the area. X times the area. Distribute that and then integrate. Let's see, what other details do I want to put in here? So a good question that I would want you to answer if we were looking at this would be, how did it go from 1 over a to having a 2 out in front? Can anyone spot that? Well, what was a? A was 1/2. And so if you take 1 divided by 1/2, that's how you get the 2. The rest of it is just integrating. We'll have 2 times the antiderivative of that, evaluated between 0 and 1. That number turns out to be 16 over 35. 16 over 35 would be, let's see, that's going to be your y bar as well because of the symmetry. So we end up with, you know, kind of a strange looking point. but it is going to be right on this center axis here. Now we've taken care of kind of two things at once. I usually separate these in my calculations. We did m sub y divided by a right here. So if you're wondering, you say, well, wait a minute, don't we need to divide here? We kind of did that part here. It's a little different than the way I do it, but it's still going to give you the right answer. 16 over 15, 16 over 35, I should say. 16 divided by 35, about 0.457. So that makes sense, somewhere around here, I'm guessing. For both x and y would be your centroid. Let's actually apply that to a different one, which would be this one up here. And this one we get to do from scratch. Thinking that this didn't copy well, this should probably be e to the x. Hopefully it's that way on your handout. Again, you want to find the centroid of this region. We'll start out by finding the area. The area of this is simply going to be what? How are we going to find the area of my shaded region? This is where you guys get to help out as well. Jesse, any suggestions?
Top minus bottom times dx.
All right, top minus bottom times dx. Since the bottom is just 0, the top is going to be e to the x minus 0 times dx. What should I integrate between? 0 to 5. Help me out here. What's the antiderivative of e to the x? Isn't that so cool? E to the x between 0 and 5. So it's going to be e to the 5th minus e to the 0. Anything to the 0 power is 1. Yay. So that's our area. Let's find the moment around the x or around the y-axis first. So m sub y. And we'll do that the same way we did the previous one. We'll draw ourselves a little slice here. For these problems, I'm always taking dx slices. So dx. This point here I'll label as x and y. The moment around the y-axis is the force that's felt by pushing down on this plate and turning this around the y-axis. So it's going to be the area of the plate times the perpendicular distance Let's find the area of the plate first. The area of the plate is going to be the width times the height. What's that going to be? What's the width going to be? Dx. And the height is e to the x. Now you could put e to the x minus 0 if you wanted to, top minus bottom, but because it's a 0, you don't really have to do that. And last but not least, times the perpendicular distance. How far away from the x-axis, or excuse me, the y-axis is this? Yeah, it's just the distance of x. So that distance is x. Let me put that here so you can kind of see where that's coming from. And let's see. That's about it in terms of that part of this. So that's going to simplify down to x e to the x dx. To find m sub y, we're going to integrate from 0 to 5. M sub y equals the integral from 0 to 5 of x e to the x dx, like that. And that's probably going to require integration by parts. So we'll leave that there for the moment. Are we okay with the setup on that one? As far as m sub x is concerned, it's going to be kind of similar. The area of the plate times the perpendicular distance to the x-axis. Perpendicular distance to the x-axis. Now that one's a little bit different because the distance to the x-axis varies depending on where you are in this plate. So we're going to regard that distance as being kind of felt halfway through. So the distance that we're going to use, we're going to assume that all the mass of this plate is concentrated right at the middle. It kind of averages it out, we'll put it right at the middle. And so this distance is going to be y over 2. Except there's one problem. When I look at my area formula, it's going to be e to the x dx. And that dx there is a nice big clue for us. What's the clue that that dx is giving us? Yeah, everything needs to be in terms of x. So I can't just put y over 2 here. What do I got to put instead? E to the x dx. Instead of y over 2, what am I going to put there? E to the x over 2. E to the x over 2, or basically 1/2 e to the 2x dx. That's my expression for m sub x. That is the force that tends to want to turn this region around the x-axis. So I'll pause there for a second. Are we okay with that one?
Where did you get the y over 2?
When you're looking at this plate and trying to figure out how it pushes down and around the x-axis, we're going to assume that all of its force is felt at that midpoint. So that midpoint would be half of the height of this function, which is going to be your y over 2. Appreciate the question. Now, to get m sub x, we're going to integrate from 0 to 5 of 1/2 e to the 2x dx. Well, the rest of this is just some grunt work. Setting it up, getting this far, is a big chunk of your points. So let me pause and make sure you're okay with where we got. You okay with finding m sub y and m sub x? I'm not seeing a whole lot of nods. You're not inspired? All right, a couple nods. All right, appreciate that. Let's do a little bit of practice finding some of these integrals. So we'll start out with m sub y. M sub y. The integral from 0 to 5 of x e to the x dx. What method is this one screaming out for? Yeah, integration by parts, and in fact we can use the table method. So let's see, let's do u and dv. Now your choice for u is typically something that is going to get easier when you differentiate. So polynomials are good choices, like x, 1, and then 0. And then something that doesn't get much worse when you integrate. Now keep in mind, your choice for dv also has to be something that you can integrate. So sometimes when you look at something and you're like, well, wait a minute, I don't know what the antiderivative is, then that might be suggesting you need to put it as a u as opposed to a dv. So e to the x, and this is just going to be e to the x again, e to the x again. Fortunately, I only have 2 of these things to deal with. What's one thing that I need to put in here so far? The signs. That one's a plus, that one's a minus, and it's going to keep on alternating from there. So the antiderivative of this thing is going to be x e to the x minus e to the x between 0 and 5. If I put in that 5, I get 5 e to the 5th minus e to the 5th minus 0 minus e to the 0. And let's see what happens with that one. Let's see. I'm trying to think if there's anything fancy I can do in terms of simplifying this. That's just going to be a plus 1 here. 5 e to the 5th minus e to the 5th. Oh, well, that could be 4 e to the 5th, right? Because you got like terms here. Let's assume that this is a 1. 5 minus 1 gives me 4 e to the 5th minus negative 1 would be 4 e to the 5th plus 1. Okay. Let's try the other one. Are we okay with m sub y here? M sub x should be a little bit more user-friendly. Integral from 0 to 5 of 1/2, which I'll write it here, 1/2 e to the 2x dx. Now it's up to you on this one, but because it kind of slows things down a little bit, I would suggest that we not try and fiddle around with a u substitution, at least formally. Let's just try and think it through and do it in our heads a little bit. Now, for myself, I always start out with, well, if I was differentiating this, I'd end up having to multiply by what? 2. Integration is the opposite of this, so if I'm integrating this, instead of multiplying by 2, I have to divide by 2. Or multiply by 1/2. It's the same thing. So the antiderivative here is going to be 1/4 e to the 2x between 0 and 5. Okay, well, let's plug in some stuff here. That's going to be 1/4 times e to the 10 minus e to the 0, or 1/4 e to the 10 minus 1. So I've got my m sub y and my m sub x. Let's put that together to find x bar and y bar. X bar is going to be m sub y divided by, well, the area. I don't think I gave that a name, did I? Let me see. Yeah, divided by the area, just a. So it's going to be 4 e to the 5th plus 1 divided by e to the 5th minus 1. There's a nice household number for you. Let's try the other one as well. M sub x divided by a is going to be 1/4 e to the 10 minus 1 divided by e to the 5th minus 1. I'd probably clean that up a little bit and just move that 4 down to the denominator. So overall it'd be e to the 10th minus 1 over 4 times e to the 5th minus 1. Kind of ugly there. If you wanted to kind of play around with these things a little bit, you can figure out that I think this is about 4.03. 4.03, and the other one is 37.35. some approximate decimal values. But overall, I'd probably be looking for an exact answer. So this is your approximate answer. Your exact answer is just these two right here. 4e to the 5th plus 1 over e to the 5th minus 1 and e to the 10th minus 1 over 4 e to the 5th minus 1. Bingo. Nice. All right, probably not the friendliest problems in the world. There's a lot that goes on. I think the physics problems are part of what makes Calc 2, you know, just a little bit harder than, say, Calc 3. And by now, I think I don't need to convince you that it's certainly harder than Calc 1. All right, so a few complacent nods there. Anything on this that you want me to wrap up on? James?
So back up to the m sub x. Is it better to leave the 1/2 inside instead of taking it out?
That's a great question. Honestly, I probably left it inside because I didn't leave myself enough room when I wrote the integral. Usually, for myself, I do exactly what you're suggesting, is take the 1/2 out in front. So, but I looked at that, I'm like, yeah, it would look really sloppy if I crammed in a 1/2 out front. So, yeah, I agree with you on that one. Thank you. Andreas, did you have a question too, or were you sympathetic nod? All right, good deal. Anything else? All righty.